Hello Internet! This is the third episode in our series about how to understand quantum mechanics. And it is time to formulate the fundamental principles of quantum mechanics. In the first episode, we learned about the general framework of a physical theory. And in the second episode, we saw how classical physics fits into this framework. You should definitely watch these previous episodes first. You may wonder why. Because quantum mechanics stands on its own and does not depend on classical physics. Indeed, quantum mechanics can be formulated and learned without any reference to classical physics. But in order not to misunderstand quantum mechanics, we must recognize and unlearn the conceptual shortcut that the mistaken assumptions of classical physics allowed us to take. Classical physics postulates deterministic equations between known and unknown quantities, diffusing the essential distinction between the observed and the unobserved, between the known and the a priori unknown. The unconscious application of this classical shortcut makes people confuse mathematical models with the physical world, causing them to misunderstand quantum mechanics. In quantum mechanics, we find that such equalities between known and unknown quantities are in general impossible. In this sense, the unobserved physical world is not commensurate with the ideas we have about it. We do not have the questionable luxury of identifying the world with a mathematical model. Instead, we must carefully distinguish between the physical and the mathematical, between the known and the unknown. We must accept that observations can give us truly new information, and we need the complete circle of prediction, observation, and update of knowledge to describe how our mathematical ideas and expectations relate to the world we experience. So let's find out how it works. Before we continue, please subscribe and comment to support the channel. It really helps a lot. This episode is split into two parts. In this first part, we will discuss the representation of knowledge in quantum mechanics. The second part will focus on the representation of a priori unknown physical quantities. Concerning the representation of knowledge, we will find a generic structure that is the same for all physical systems. This structure expresses the rules of a new extended version of probability calculus. Concerning the representation of unknown quantities, we will find the most central innovations of quantum mechanics. This latter part is where the interesting differences between particular physical systems can be formulated. Quantum mechanics is a logically closed theory. It is not derived from anything else, and any starting point for explaining it is somewhat arbitrary. A true leap of discovery was needed to find quantum mechanics, and to learn it, we still must be willing to take a certain mental leap, start with one of the postulates, and accept some apparent logical gaps until the full internally consistent theory has been established. We will start our discussion at the one point that is familiar to our experience, at the empirical foundation of physics, our observation of the physical world. No matter how profound revolutions in theoretical physics might be, there is no discontinuity in experimental physics or in our everyday experience of the world. There is nothing new in the fact that we observe or in how we observe. What changes with our theories are our assumptions about what we can possibly observe at all and in principle. Let's return to our example of observing a particle with position x and momentum p. In classical physics, we imagined that we can eliminate the uncertainties delta x and delta p simultaneously. Quantum mechanics replaces this assumption with the so-called uncertainty principle, which expresses a fundamental limit of experience. The uncertainty principle says that for all possible observations of position x and momentum p, the product of the uncertainties delta x and delta p will be at least h bar over 2, with h bar denoting the reduced Planck's constant. Ultimately, we will not take the uncertainty principle as a postulate. We will later show that it is a consequence of the mutual relationship of the a priori unknown quantities uppercase x and uppercase p. The uncertainty principle implies that beyond a certain level of accuracy, we must choose which quantity we want to know precisely, trading off the uncertainties against each other. The more precisely we pin down the position of the particle, the less precisely we can discern its momentum and vice versa. Going to the extremes, we can still imagine the uncertainty delta x of the position to go to 0. But then the momentum will be completely unknown. Vice versa, we could in principle reduce the uncertainty delta p of the momentum to 0, but then the position will be completely unknown. Whatever we do, we can only ever know one of x or p precisely. This choice that the observer must make between observable quantities is an essential aspect of how quantum mechanics describes the world. And the necessity of this choice makes it impossible to have a general system of equations between known and unknown quantities like the one we had in classical physics. Which choices are available to the observer? The full answer will be given in part 2. For now, we will just define that if there is no obstruction to knowing a given set of observables simultaneously, we will call these observables compatible with each other. For a set of compatible observables, quantum mechanics still allows us to imagine an idealized observation that gives us exact knowledge of these quantities simultaneously. If we cannot know two quantities simultaneously, even in principle, we call them incompatible or complementary. In our example, the position uppercase x and the momentum uppercase p are complementary to each other, and either uppercase x by itself or uppercase p by itself constitutes a complete set of compatible observables. Consequently, we can no longer represent our knowledge about the particle by a classical phase-space point x, p, as that would imply certain knowledge of both quantities. Thus, quantum mechanics requires a new way of representing our knowledge that takes the irreducible uncertainty in complementary observables into account. So how can we represent our knowledge according to quantum mechanics? Let's choose to measure the position x precisely, letting its uncertainty delta x go to 0. Here's how quantum mechanics tells us how to represent our knowledge. First, we need to list all the possible distinguishable results we can get for the chosen observables. In our case, we list all possible positions lowercase x. X can be 2 centimeters or 2.5 centimeters or 3 centimeters or 3.5 centimeters and so on. For reasons that will become clear later, such a list is referred to as an eigenbasis of the chosen compatible observables, and each possible outcome is called a common eigenstate of these observables and is denoted by a cat symbol with a vertical bar and an angle. The potential result itself is called an eigenvalue of the corresponding observable. But don't let the terminology intimidate you. This is really just a list of outcomes that can be distinguished by the results of the chosen compatible observable quantities. Such an eigenbasis is a maximal list of distinguishable physical situations because it covers all possibilities, and due to the complementarity of the other quantities, we cannot have any additional knowledge in each case. However, an eigenstate does not represent certain answers to all the questions we can ask about the system, because the complementary quantities, in our case the momentum, remain uncertain. Now we are ready to perform the actual measurement. Let's say we measure a position of x equals 3 centimeters. We represent the certain knowledge that the position has been measured as x equals 3 centimeters by writing down a column of numbers with a 1 at the measured position and zeros everywhere else. This column of numbers is called the wave function, and it represents maximally precise knowledge of the physical situation. The individual numbers are called amplitudes. Symbolically, we will write psi of x for the amplitude corresponding to position x. This is literally what the wave function is. It is an amplitude 1 marking the result we have observed. There is nothing more to an individual wave function than that. In particular, there is nothing weird or strange or even essentially wave-like at all about the wave function. There is no description of physics in an individual wave function beyond the pure recording of our observational result. It is just the same as marking the result we got in the list of possible results. Importantly, the wave function is only meaningful with respect to the basis it refers to. In our case, we picked the position basis, so the wave function is a function of position. If we had picked the momentum basis, our wave function would be a function of momentum. And in general, the wave function is a function of the chosen complete set of compatible observables. There is something obvious to get out of the way. As we imagine an arbitrarily precise measurement of the position, there are infinitely many possible results we can distinguish from each other. Our wave function therefore encodes infinitely many amplitudes, one for each possible result x. Knowing one exact position with certainty corresponds to a wave function with an infinitely sharp peak at that position and an amplitude 0 everywhere else. A mathematically precise treatment of such singular wave functions is possible, but it comprises some technical difficulties. As these technical difficulties are of no conceptual interest here, we will simply ignore them and mostly pretend to have a finite set of distinct possibilities to work with. While there is nothing remarkable about an individual wave function, quantum mechanics makes some interesting postulates about the collection of all possible wave functions. More concretely, it says 3 things. Wave functions form a complex vector space with a well-behaved inner product. These points can be summarized in the statement that wave functions represent vectors in a complex Hilbert space. Let's look at these 3 points in turn. First, complex. So far, we have only used the amplitudes 1 and 0. But there is some additional freedom I have not yet mentioned. The amplitudes are to be regarded as complex numbers, and instead of the number 1, we may use any complex number of absolute value 1. We may use -1, the imaginary unit I, or any other number on the complex unit circle. As the other amplitudes are 0, this choice amounts to multiplying the whole wave function by an arbitrary complex number of absolute value 1. In other words, we can choose an arbitrary phase factor for the wave function. This overall phase factor has no physical significance whatsoever. It is just an arbitrary choice in our representation of knowledge. Just like choosing different colors to mark our observational result. At this point, the phase factor appears to be a needless redundancy, but we will see later that overall, the appearance of complex phases is essential to quantum mechanics. Second, vector space. The amplitudes with respect to a chosen basis specify the representation of our knowledge as a vector in an abstract vector space, which we will denote by script h. We can write this vector as a linear combination of the basis vectors using the amplitudes as coefficients. The resulting vector is a basis-independent representation of our knowledge, and the amplitudes psi of x are simply the coordinates of this vector with respect to the chosen position basis. The vector space axioms tell us that we can write any generic vector uppercase psi in H by choosing suitable amplitudes with respect to the basis we picked. The sum of two such vectors then is the vector we get by adding the corresponding amplitudes with respect to the same basis. In general, we can form linear combinations of vectors by multiplying each vector by a complex coefficient and adding the results. Even if we start out with only a basis of eigenvectors of our compatible observables, we can use linear combinations of the basis vectors to build vectors with arbitrary wave functions. Can we regard such generic vectors as representations of knowledge too? The answer is given by a fundamental postulate of quantum mechanics known as Born's rule. In its simplest form, Born's rule states that the vector with wave function psi of x with respect to an eigenbasis of the observable uppercase x represents the knowledge that the probability that the physical situation corresponds to the outcome lowercase x is the absolute value of the amplitude psi of x squared. This calculation of probabilities from complex amplitudes is one of the central innovations in quantum mechanics. Note that Born's rule cares only about the absolute value of the amplitude and ignores its complex phase. Since all physical predictions ultimately go through Born's rule, this means that the complex phases are in principle unobservable. We will soon see, however, that the complex phases do play a crucial role in calculating amplitudes and thereby probabilities with respect to complementary quantities. Born's rule gives us a straightforward restriction for vectors that are to be interpreted as representations of knowledge. Since the total sum of probabilities for all possible alternative outcomes must be 100%, we must demand that the sum of the squared absolute values of all amplitudes be equal to 1 for such a vector. Vectors with this property are called unit vectors, and by Born's rule we can interpret any unit vector as a representation of maximal knowledge about the physical situation. I can hardly emphasize enough how crucial a postulate Born's rule is. It is only through Born's rule that quantum mechanics becomes a physical theory. Any connection whatsoever between the mathematical representation and its physical interpretation goes through Born's rule in one form or other. Born's rule is the physical interpretation of quantum mechanics, and it is a necessary and sufficient rule that encapsulates all we can say about the a priori unknown physical world. It is good to check the consistency of Born's rule with our statements about the representation of knowledge by the wave function. We represent certain knowledge by entering an amplitude of absolute value 1 for our observational result and zeros otherwise. According to Born's rule, this implies that the probability to observe the result that we got is 100%, that is certainty, while the probability to observe any other outcome of the same compatible observables is 0%, that is impossible. We conclude that our rule for the wave function, together with Born's rule, is consistent with the defining property we demand of knowledge, namely reproducibility. In principle, if we immediately check the knowledge we recorded in an idealized perfect observation, we will receive its confirmation with certainty. In other words, Born's rule works both ways. It gives us the physical interpretation of generic unit vectors, and it also singles out the eigenstates as the vectors to use to represent certain knowledge about a quantity. You may wonder whether the admittance of generic unit vectors invalidates my earlier claim that the wave function is nothing but an amplitude 1 picking out one of the possible observational results. After all, a generic unit vector may have any number of non-zero amplitudes. According to Born's rule, a vector with more than one non-zero amplitude represents uncertainty in the quantities corresponding to the chosen basis. For example, here we have a wave function predicting an uncertain position with a 50% probability of the position x to be 3 cm and a 50% probability of the position x to be 4 cm. In which sense does such a wave function represent maximal knowledge? Such vectors with more than one non-zero amplitude are often called superpositions of multiple basis vectors. However, these so-called superpositions aren't any more special or any more general than the basis vectors themselves, because we must always remember that amplitudes are only defined with respect to a chosen basis. The same vector that is a superposition representing uncertain knowledge with respect to one basis is a basis vector representing certain knowledge with respect to a different basis. All unit vectors are equivalent in this sense. For a generic unit vector psi, we can always change to a basis in which psi is one of the basis vectors. This new basis is an eigenbasis of some other observable A. The vector space axioms guarantee the existence of this observable and of a suitable eigenbasis. For example, we may find that the same vector that represents an uncertain position x represents certain knowledge that the observable A has the definite value A sub 1. Importantly, which vector we get in the A eigenbasis depends on the relative complex phases of the amplitudes in the X eigenbasis. For example, by negating the phase of the amplitude for x equals 4 compared to the one for x equals 3, we may get a vector psi prime that represents A equals A sub 2 instead of A sub 1. With respect to the observable x, both the original vector psi and the vector psi prime represent the same uncertain knowledge about the position, while with respect to the observable A, they represent different certain knowledge about the value of A. Note that we can speak about relative phases, which are differences in phase, only because there are multiple non-zero amplitudes with respect to the position eigenbasis. That is only because there is uncertainty about the position. Thus, uncertainty about one observable is the precondition for having certainty about another complementary observable. It is this change of basis, rather than the wave function itself, in which we find interesting physics like the wave-like qualities of particles, typical of quantum mechanics. The formulae for changes of basis are determined by the mutual relations of complementary quantities, on which we will focus in part 2 of this episode. Third, the inner product. Any two vectors, phi and psi in H, have an inner product with each other, which is a complex number written as the bracket of phi with psi. The inner product is a basis-independent number. It depends only on the two vectors and not on the basis we use to represent them. But a smart choice of basis can make it easier to calculate this number. Quantum mechanics postulates that the inner product has some nice properties, the details of which you can look up in the notes. These properties imply that we can always choose our basis such that the inner product has the following simple expression in the wave functions of phi and psi. For example, in the position basis, the inner product is equal to the complex conjugate of phi at one position times psi at the same position plus the complex conjugate of phi at the next position times psi at that position, and so on. Note that this is only a slight generalization of the inner product of real vectors we learn about in high school. A basis in which the inner product takes this simple form is called an orthonormal basis, for reasons that will soon become apparent. The physical interpretation of the inner product is given by a more general form of Born's rule. It states that knowing psi, the probability to observe the outcome represented by phi, is the absolute value of the inner product of phi with psi squared. This connection between probabilities and the inner product is fascinating, because it means that the abstract geometry of the Hilbert space H, encoded in its inner product, expresses the rules of a calculus of probabilities. as we will see, these rules reproduce traditional probability theory, but they also go beyond it in interesting ways. If the inner product of two vectors is 0, we call these vectors orthogonal to each other. By Born's rule, such orthogonal vectors represent mutually distinguishable physical situations. If we have certain knowledge of one of these situations, the probability to observe the other is 0. Orthogonal vectors represent distinguishable alternatives. Note that distinct basis vectors in an eigenbasis of a complete set of compatible observables must be orthogonal in this sense, since they represent outcomes distinguished by different values of these quantities. By the properties of the inner product of any vector psi with itself is a non-negative real number. We use this to define the norm of the vector psi by prescribing that the squared norm of psi is equal to the inner product of psi with itself. Unit vectors are exactly the vectors of unit norm. You can check that this basis-independent definition coincides with our earlier definition of unit vectors in a position basis. The eigenbases we choose to work with are called orthonormal, because distinct basis vectors are orthogonal to each other and each basis vector has unit norm. This corresponds to the physical statement that each basis vector represents maximal knowledge of the physical situation and that different basis vectors represent outcomes that can be distinguished with certainty. As in any Hilbert space, the famous theorem of Pythagoras holds for orthogonal vectors. The squared norm of the sum of two vectors is equal to the sum of their squared norms. This is important because it means that we can interpret the addition of vectors in the Hilbert space H as representing a logical OR disjunction, and the resulting probabilities obey the well-known statement from probability theory that the probabilities of mutually exclusive alternatives are to be added. Thus, quantum mechanics reproduces traditional probability theory for non-overlapping, that is, distinguishable situations. However, for non-orthogonal states, quantum mechanics makes strictly more interesting predictions than the old-fashioned probability theory. If you want to know more about this topic, check out my video about the meaning of plus in quantum mechanics. In the generic case, two vectors phi and psi in the Hilbert space H will have a non-zero inner product with each other. By Born's rule, this means that knowing psi, there is a non-zero probability to observe the outcome represented by phi and vice versa. Consequently, the physical situations represented by the two vectors cannot be distinguished with certainty. This is not merely a statement of similarity. Rather, there is a non-zero probability that the physical situations represented by the two vectors are exactly the same. This is a genuinely new idea introduced by quantum mechanics, and it means that the Hilbert space H is not an analog of the classical phase space. In classical phase space, 2 points represent either exactly the same physical situation or two certainly different physical situations. Classical physics therefore allows us to think of phase space as the mathematical set of all possible physical situations. In quantum mechanics, we cannot make an analogous assumption. While two vectors in the Hilbert space H are mathematically either the same or different, this is not true of the physical situations represented by these vectors. We cannot assume the existence of a canonical set of all possible physical situations, because one defining property of a set is that two of its elements are either the same or different. Now you see why it is so important to distinguish between mathematical and physical concepts. Mathematically, phi and psi may be different vectors, but the physical situations about which they represent maximal knowledge cannot be distinguished with certainty. Consequently, we cannot draw a complete and exact picture of the physical world, because two pictures are either the same or different, which does not do justice to the nature of the physical world. There are a lot of confused discussions about whether the wave function constitutes only knowledge about the physical situation, or whether it is the physical situation. So let me say a few words about that. Everyone will have to agree that the wave function, which by Born's rule implies empirically verifiable statements about the physical system, is at least knowledge about the physical system. So the remaining questions are: is there a conceptual distinction between the wave function and the real physical state? Is the wave function something beyond knowledge about the physical state? And what would that something be supposed to be? Philosophers love to throw around the E word and the O word in this context. You should be very careful with these nasty terms, because as soon as you accept them, you are trapped into a false dichotomy between knowledge and reality, which will keep you from understanding quantum mechanics. We are used to make this distinction in everyday life, mostly because our knowledge is usually approximate and unreliable. We should honestly call it a blurry expectation rather than knowledge in most cases. But the situation is very different in the context of a fundamental physical theory. In quantum mechanics, we speak about precise and maximal knowledge that has certain implications. There is no reason in this context that forces us to categorize notions as signifying either knowledge or reality. Quite to the contrary, if you think sharply, you will find that these notions merge, and that knowledge is as real as anything you can hope to define, with reality being operationally defined as reproducibility. Is there something to observe beyond the maximal knowledge represented by the wave function? If not, all future results would in principle be known with certainty. Once we'd have maximal knowledge, we could never learn anything new. That would be classical determinism. In quantum mechanics, the answer is yes, there is something to observe beyond maximal knowledge, namely true randomness. And observations can give us truly new knowledge. For many people, this seems hard to accept, but if you think carefully, true randomness is by definition the only valid complement to maximal knowledge. It is also worth noting that it is not meaningful here to distinguish between knowledge per se and knowledge about something. Once we are dealing with a truly fundamental description of nature, the notions of being and behaving merge. All we can say is what we can observe and which correlations hold between our observations. Quantum mechanics makes no claims about any implications of the wave function beyond Born's rule, and if you analyze the theory carefully, you find that any additional claims would cause inconsistencies. The meaning of the wave function is precisely the knowledge implied by Born's rule. Nothing less, nothing more. To summarize, in a fundamental theory dealing with maximal knowledge, there is no meaningful conceptual distinction between knowledge and reality. There is nothing to know beyond the maximal knowledge represented by the wave function. There is something more to observe, though, the true randomness manifesting itself in observable quantities complementary to those we know with certainty. We need one final step to complete our discussion of knowledge: the update of our knowledge after we have first made predictions and then made an actual observation. This update is a simple step that comes down to entering an amplitude of 1 in a column of numbers and setting the rest to 0. But it has been given an overly dramatic name. It is called the collapse of the wave function. That's quite an extravagant way of stating the obvious. Whenever we gain new knowledge by observation, it narrows down the outcomes we had considered possible to the one actually observed. This so-called collapse is not a physical process. It merely acknowledges mathematically that outcomes of observations give us truly new knowledge that we did not have before. Even though this update of knowledge is not a physical process, one might rather call it an act of consciousness for lack of a better term, it is an essential part of quantum mechanics as a physical theory. Note that it naturally adds an element of irreversibility to the theory. Knowledge, once obtained, may become obsolete later, but it cannot be unseen. The reason why people struggle with the collapse of the wave function is that they misunderstand the role and meaning of the wave function. Here's the wrong picture they supposedly have in mind. They imagine the wave function as a picture of the unobserved physical object, which has to mysteriously and physically collapse in order for us to observe an actual result. This is completely wrong. There is no correct picture of the unobserved physical world. The wave function is not a physical object. It is not composed of observable but as of yet unobserved quantities. Quite to the contrary, the wave function always represents knowledge about already observed quantities. It is the result of observation, not its object. The arbitrary overall phase of the wave function and some redundancy in the relative phases we still need to discuss should serve as a constant reminder of the unobservability of the wave function. The only link of the wave function to physical observations is in the statement of Born's rule, the prediction of probabilities of observational outcomes for a priori unknown physical quantities. But how do we represent these unknown physical quantities? That will be the topic of part 2 of this episode. So far, we understand the representation of knowledge in quantum mechanics. Maximal knowledge about the physical system is represented by a unit vector in Hilbert space, with an inner product that expresses probabilities according to Born's rule. Importantly, the structure of this Hilbert space is essentially the same for all physical systems. Only the dimension of the Hilbert space, which is equal to the number of physical situations we can simultaneously distinguish, depends on the particular system. Any two Hilbert spaces of the same dimension work exactly the same way. This universality of the Hilbert space structure in quantum mechanics should not surprise us too much, as we have already recognized that this structure expresses the rules of an extended version of probability theory. And this calculus of probabilities is the same for all physical systems. It's an expression of the rules of logic in their most general form, rather than an expression of particular physical laws. All specific properties of a physical system are encoded in the mutual relations of a priori unknown observable quantities. These relations are what we will discuss in part 2 of this episode. If you have any questions about this video, please post them in the comments below. If you liked this video, please comment and subscribe. See you in part 2.